Hello everyone, let's talk about another medium problem on Leetcode today. Subarrays sum divisible by k, Leetcode 974. In this, we are given an integer nums and an integer k. We have to return the number of non-empty subarrays that have a sum divisible by k. A subarray is a contiguous part of an array. So in the first example, we can see that nums is equal to 4, 5, 0, minus 2, minus 3, and 1, and then k is equal to 5, and then the output is 7, and the reason is we have following subarrays whose sum is actually divisible by k. Take for example this subarray 4, 5, 0, minus 2, minus 3, 1. Like the whole subarray, actually when we sum it up, we actually get 5 as the sum, right? And 5 is actually again divisible by k, which is equal to 5. Then we have a single element 5, which is this one, is also divisible by 5. So this is one subarray. Then 5 and 0 again is divisible by 5. Similarly, you notice that 0 is also divisible by 5. So these are all the subarrays where actually sum is actually divisible by 5. Now that we have seen the examples, let's jump into the solution space. The brute force approach to solve this problem will be that we actually create all the subarrays from the given arrays and then calculating the subarray sum and check if it's actually divisible by k. So that will take O of n square time because we will be running two nested loops. Another approach can be that we can actually use the prefix sum because prefix sum helps us in getting the subarray sum. So if we have prefix sum between two indices of the given array, then the difference between them actually gives the sum of the subarray between index I and j. But prefix sum in itself will not be sufficient because we will also need modulus operator with it. If you remember, we have already seen this in the continuous subarray sum problem, that the subarray sum is divisible by k when the remainder of the prefix sum is equal at two different indices. So in that we have seen if there are two numbers x and y and we apply the modulo operator on them, and if the remainder is same, that means difference between them is actually divisible by k itself. And the reason was like we can represent x as a plus m into k, that is a plus some multiple of k, right? Similarly, y can be also represented in such a way that it is a plus some multiple of k, and the difference between these two will be like a will cancel out and we will have some multiple of k remaining. So suppose x is equal to 100 and y is equal to 2 and then k is equal to 7. So the modulo operator is same, but the difference between 100 and 2 is 98, which is again divisible by 7. So if you want to see the detail of it, please go and check it out, that video. Now let's look at how prefix sum modulo k will work. So let's take nums array and k from example 1. So this is how we will calculate the prefix sum. 4 plus 5 is 9. 9 plus 0 is 9 again. When we do minus 2, we get 7. Then with minus 3, we get 4 and then 5 eventually. But when we apply the modulo operator, this is how the prefix sum modulo k we will get. And now let's try to see the pattern there. So if we see, when we saw the first 4, that was okay, but when we see 4 again, that means whatever is a sub array here is actually divisible by 5, right? Because that's what we saw in the previous slide, right? So in this case, we can see that 5 is actually divisible by 5. So this is one sub array. Then we again see 4. So that means whatever we have as a prefix sum so far is actually divisible by 5. So we can see that this is also divisible by 5 because 0 is divisible by 5. Similarly, this sub array is also divisible by 5. So we got two subarrays. So far we got like three subarrays because of that. So this is how we will actually discover the subarray based on this prefix sum modulo k. Now let's do the full dry run. Initially we will be processing number 4. Then we can see that we couldn't find any pattern because we started with 0, but now the prefix sum modulo k is 4, so we don't find any match. So we will just continue. Then number is 5, right? And we see that actually the prefix sum modulo k now match. That means this is a subarray we have counted. So our count becomes 1 and we have found one subarray now. Now num is equal to 0. Our prefix sum is 4 again. But we have already seen prefix sum 4 now twice, right? So that means we have found another subarray. So this is one subarray we had found, and then again we are finding it here. So that means now we have three subarrays because one was subarray with 0, the new element that we found. Then we found the subarray where the previous prefix sum occurred, that is this one. So we found 5 and 0 again, and 5 was anyways earlier added. So now our count actually becomes 3. So again we continue. This time our number is -2, right? But our prefix sum is 2. We have not yet seen it, so all good. We will just continue to the next number. So this time number is equal to -3. The prefix sum again is 4, but we have already seen prefix sums earlier. So that means whatever is the prefix sum here, so we found one subarray here. So -2 and -3 are one thing. Then we also include -2, -3, and then 0, right? Because this is where we found one more subarray where actually the prefix sum is matching. And then another one is this one, right? Because we also need, I think it's getting cut here, but basically it will be 5, 0, -2, -3. So this is the subarrays we have found so far. So our total subarrays now become 6 because this is the current count we are at. So then we continue and go to the next number. Now we are at number equal to 1. Now we see prefix sum as 0, but 0 we have not seen so far, right? In the prefix sum mod key. But actually this is an edge case kind of a thing where 0 is also divisible by 5. If you have come to this point, that means this is also one of the subarrays. So we will add 4, 5, 0, -2, -3, -1 as one of the subarray. And now our count becomes 7. Now that we are done with all the numbers, we will return the count. Also, one more thing we have to consider is how we will handle the negative numbers. When we apply the modulo operator on the negative number, we should also add k to it in some programming languages. Because, for example, in Java, when we apply the modulo operator on, say, -1 modulo 5, we get -1. But actually, the remainder cannot be negative, right? It should always be positive. So that's why we add k. In some programming languages like Python, when we apply the modulo operators on the negative number, we actually get correct answer. In this case, it is 4. And the reason for this is, if you remember, when we do the modulo operators, say we say x%k is equal to a, that means x can be written as k into n plus a, right? So if we try to apply it in the below equation, so we know x is equal to -1. We know k is equal to 5, right? We don't know the multiple yet, but what is the minimum multiple we can get, which is negative, is -1 in this case, and then we have to add the minimum value to it. We don't know yet, so it will come out to be a equal to 4, right? This is the correct way of calculating the modulo operator with the negative numbers. So the idea is that a should always lie between 0 and k minus 1. Now let's look at one more example. So if we do 11 modulo 7, we get 4. But if we do -11 modulo 7, we get 3. And the reason for this is again the same. We set -11 equal to 7 into minimum multiple of 2, which is just less than 11. That is -14 in this case. To balance it out, we need +3. So that's why +3 is our remainder. So now let's jump into the code part. So first thing we will do is we will create a map to track the number of times we have seen prefix sum modulo k, because as soon as we see it, our number of subarrays actually increase for us. Then we will put map dot 0, 1. This is to handle the edge case that we saw when the subarray sum becomes 0 and 0 is also divisible by k. Initially prefix sum mod k will be equal to 0 and count will be our answer, and that is also equal to 0. Now we will start counting by looping onto the numbers. First thing we will do is we will update our prefix sum mod k whenever we see a new number. So it will be equal to prefix sum mod k plus num%k, right? And if number is negative, we will just add a k to it and just apply modulo operator on it again. And now we will get the current count we had so far. So we will now get the count of the prefix sum modulo k operator we have seen so far. And increment the count based on it. If it's not present, we will just return 0. Then we will just do count plus equal to current count. So now because we have seen it one more time, we will just increment the value of current count by 1. So first time we encountered 4, but then we again see 5, but the prefix of modulo k was 4, so we are encountering it for the second time, and that's why we will also increment the count based on it. Once we process all the values in the nums, we actually return the count. Now let's try to run this code. Cool, let's submit. Coming to the time complexity, because we are processing n numbers at a time, the time complexity is O of n. And in terms of space complexity, it will be O of k, because we are storing prefix sum modulo k, and we already discussed that the remainder when we do the modulo k will lie between 0 and k minus 1. So that's why at max there will be k elements in the worst case. I hope this video was helpful to you. If it was, please like and subscribe and comment on how I can do better. Thanks again. Have a nice time.